Welcome back to class, everyone. Grab a seat. Today's explainer focuses on an absolutely foundational concept of object-oriented programming in Python, and that is mastering inheritance. Now, as computer science students, you've already learned how to build your basic blueprints using classes and objects. But today we are going to level up. We're going to see exactly how we can make our code incredibly efficient, reusable, and so much easier to maintain. Here's our syllabus for today's explainer. We'll start with inheritance in the real world, why we actually need it, the syntax and code reusability, overriding methods and logic, some common mistakes with a superfunction, and finally, a summary checklist.
All right, Section 1, Inheritance in the Real World.
Let's step away from the code for just a second. In reality, inheritance is something we are all intimately familiar with, right? We inherit physical properties and wealth, like maybe a family business. We inherit physical appearances. You might have your mother's eyes or your father's nose. We even inherit specific behavioral traits from our parents or grandparents. Have you ever reacted to a situation and thought, wow, I sounded exactly like my dad just then? Maybe it's a specific way you handle stress, or even short-tempered anger issues. It's literally in our genes to inherit what our parents have and what they do.
While it is truly fascinating how directly this human genetics analogy maps to Python programming. In object-oriented programming, classes are our blueprints. Attributes are what an object has, and methods are what an object does. So inheritance in programming is simply the ability to absorb those exact attributes and methods from an already created class right into a newly created one. Now, just to keep our terminology strict for your exams, we formally define the existing blueprint, the one we pull features from, as the base class. You'll also hear it called the parent or superclass. On the flip side, the new blueprint that is absorbing those traits is the derived class, also known as the child or subclass. Moving on to Section 2, why do we need inheritance? Understanding the why is basically half the battle in computer science. So think about this scenario. Imagine we're building a simulation with a male class and a female class. Since both are human, both need the ability to eat and the ability to work. So shouldn't we just explicitly write the eat and work methods into the male class and then copy and paste them over into the female class? The answer to that is a hard no. Writing code from scratch twice is a massive waste of time, and it bloats your program unnecessarily. Inheriting those common methods prevents redundant code, it decreases the total lines you have to manage, and it massively increases code reusability. And let me tell you, on large industry projects where you have dozens of interconnected classes, this drastically improves maintainability. If you need to fix a bug in how humans eat, you want to fix it in one single place, not 50. Okay, Section 3, syntax and code reusability. Let's look at the actual code. The syntax for this in Python is incredibly straightforward. You write the class keyword, followed by your new derived class name. Then, instead of just a colon, you open a set of parentheses and simply pass the base class name right inside them. It's essentially telling Python, hey, build this new class, but start by copying everything from this existing one. This brilliantly illustrates the difference. Look at the bad way on the left. We have a standalone male class where we manually type out the eat and work functions. Now look at the good way on the right. We already have a human class defined elsewhere that knows how to eat and work. So the male class simply passes human in parentheses. We use the pass keyword because, well, we don't even need to write any new lines right now. It automatically inherits those eat and work methods directly from the human base class. Section 4, overriding methods and logic. But what happens when the child class needs to do things a bit differently than the parent? Just like you might have your own distinct way of doing things compared to your parents, you have your own identity, a derived class can have its own specific behavior too. A child class can override a base method simply by redefining it. Here, the human class might say, I can work, but we redefine the work method inside the male class to output I can code. We've completely overruled the parent's definition.
But wait, what if we don't want to completely erase the parent's logic? What if we want the parent's logic and our own extra feature? This is where a very special Python function comes into play, the super function. Calling super gives you direct access to the parent class. So inside our overridden work method, we call super.work to fetch the original behavior, and then we add our custom statement, print I can code.
By doing this, when we actually run our program and call the work method on our derived object, it prints both. It prints the inherited parent logic, I can work, and then perfectly follows it up with the specific overridden child logic, I can code. This is just an incredibly powerful way to extend functionality without rewriting your existing systems. moving to Section 5, Common Mistakes with Super. Now, I need you all to pay close attention because we're going to do a live debugging of the most common trap beginners fall into. I literally see this mistake in your assignments all the time. Let's say our base human class has an initialization function, an init method that sets attributes like the number of eyes or the number of hearts. Notice the crucial warning here. If our derived male class defines its own init function just to add a specific attribute like name, it completely overwrites the parent's initialization. You suddenly lose access to the base attributes. Programmatically speaking, your human male no longer has eyes or a heart. To fix this, you have to call super.init inside the child's initialization. But students often follow this exact sequence of mistakes. First, they create the custom init. Second, they correctly call super.init. But third, they completely forget that the parent class actually required a specific parameter, like a variable for num_heart. When they fail to pass that data up the chain, boom, the system throws a very frustrating type error.
And here is exactly what that error looks like in your console. Missing one required positional argument. So the crucial takeaway here is this. If the base class expects an argument like number of hearts, your child class's super_init call must pass that exact positional argument upward. You absolutely have to feed the parent class the data it needs to build itself, or your entire program is going to crash.
All right, Section 6, Inheritance, a summary checklist.
Let's wrap up today's lecture with a final checklist for your future programming projects. First, always identify shared features early to avoid writing them from scratch. Second, put those common methods into a base class. Third, when creating your specific blueprints, pass that base class into the derived class's parentheses. Fourth, make sure to use the super function if you want to retain parent logic while adding your own flair. And finally, always ensure you pass required positional arguments to your super_init calls so you don't lose those crucial base attributes. This is exactly how you keep your code reusable, highly maintainable, and completely bug-free.
Class dismissed, but I'll leave you with this final thought to ponder before our next explainer. If inheritance lets us build these incredible, deep, nested hierarchies of code where objects inherit from parents, who inherit from grandparents, and so on, at what point does that massive family tree of code actually become more confusing to trace than it is helpful? It's a very real architectural challenge in software engineering. Think about that, and I'll see you in the next one.